Oh, if you just watch Khan Academy, there's a lot of good stuff there too.
If you watch what?
Khan Academy, KHAN Academy.
Yeah, they have some really good calculus videos, man. If you're into the upper levels of calculus, really good levels.
Oh, everything. The guy does everything from evolution to molecular biology to quantum physics to whatever. It's interesting. All right. So what we'll do today is to take a look at the homework assignment, because I think we'll be done today, and then I'll give you guys another week to finish the homework assignment. Okay? Because I think we're pretty close already, and it's just one last piece that we have not talked about to finish it. And I have done some grading over the weekend. It's just the first homework assignment, the standard in-out homework assignment. But it's really interesting, just even reading the code from everybody for that homework assignment. It's kind of interesting. I can actually see different types of programming styles. Some people are more verbose. Other people are very terse. And just very to the point. Okay, the logic is correct, and that's it. Okay, 3 lines. If 3 lines can do it, 3 lines is it. And then there's some people using a more kind of like a scenic route. There's nothing wrong with a scenic route in a class, because we are all here to learn how to do it. So as long as it is correct, and you learn the concepts along the way, it's good to go. And then there are some that has absolutely no chance to work.
Yeah. I hope that wasn't mine.
Did you have to single mine? Did you have to single mine out?
Well, I mean, there was one that did not even use read or write. So to me that was kind of like a little disappointing, because the homework assignment, did state to use the read and the write functions, and that's the whole purpose. Is how do you interface with the operating system? Is the read and the write operations. So there's a good variety. I'm kind of looking forward to read the MBR homework assignment too.
So can we view it online now?
The grade is online. For the first one is online. The infrastructure one I haven't really graded yet, because that one is pretty just structural stuff. All right. So we'll go ahead and take a look at our current topic. Raw extension to access. And as I said, I'm going to give you guys a picture today. So let's go ahead and open up all the tabs. All right. So this is what I would use as my tool. Let me see, where is it? I think it's under Office. It's called FreeMind. The program is called FreeMind, and it's a Java program, which means it's definitely cross-platform compatible. And what it does is really just capturing concepts, in a kind of semi-structured way. I learned about this program when I have to teach my 6-year-old, how to organize ideas for papers, like history papers that she has to write and stuff like that. So what we'll do is we'll use the same concept here, and we'll start with a superblock. Okay. All right. The superblock has a particular structure, and there are several things here that are definitely useful. Knowing the inodes count is useful. This is the total number of inodes in the entire file system. Okay, that's going to come in handy at some point. So what we'll do is we'll go ahead and capture that. So we'll just go ahead and insert inode count. So I'm just going to record, things that I think I'll need. Okay, blocks count is the total number of blocks in the file system. That may not be very useful in our case, because I don't think we'll need it for this homework assignment. Free blocks count, free inode counts. Now these are useful if you want to check whether your file system is still valid or not, because you can basically, track down everything that is known to be a file, and then check, at the end of the day, you can check, the number of inodes that are free, the number of blocks that are free, versus what, the system reports that should be free. And if there's a difference, you have a problem. Yep.
So is the inode count, is that how many are available, or is that how many are used?
How many total is, what is the capacity of the entire system? Yep. So it's not the amount that is free. The next one, this one tells you how many inodes are supposed to be free. Okay, but there are reasons, if your file system is corrupted, it is possible that it's reporting a number that is larger or smaller than it should be. The free count can be off, and that's why sometimes when you run e2fsck, it will say that certain things are adjusted, including the number of free inodes and so on. Okay, the next one is the first data block, which is kind of useful, but we don't really need to use it here. The log of the block size is going to be useful, so we'll go ahead and record that too. What was that again? Block size. The flock. Interesting elementary school topic. Find all the words that rhymes with block. Okay, fragment size, blocks per group. Now that can be useful, but not really in our homework assignment, because fortunately what we are looking for is always in the first block group. So the number of blocks per group is not as useful, but we'll keep track of it too. Oops. Place blocks per group. Okay, so right now we have several terms already. We have the superblock as a term. We have inode as a term. We have block as a term, and then we have block group as a term as well. So right now, how are all of these things organized? So let me see if I can use a spreadsheet for that purpose. Under Office, Calc. Now this is strictly for illustration purposes, and nothing is to scale. We'll go ahead and save the file first to today's folder, which I have not created yet. It's 227.
Do you have plenty of room for the recording?
I think so. We have 3.6 gigabytes, good for 3 hours. All right, so if we look at, okay, let's shrink it a little bit. I know it gets a little bit harder to read, but it's easier this way. Okay, so if we look at this entire thing as the file system, or the entire partition, let's take a look at how those terms relate to each other. So we'll go ahead and, okay, this is what I'll do. I'll just use a borders, to indicate the outline of this thing. Okay. That doesn't show. Format cells. There we go. Okay, so this is the entire partition. In other words, you can look at the entire partition as if it is just one huge array of blocks. Okay. But the first thing you have to do is to go find the superblock. The superblock, is somewhere, in the first part of the entire thing, but it's not exactly the first, because it's not at location 0 of the entire partition. It is at location 1024 of the partition. So we'll just, but we'll just say the superblock is here. Can people in the back still kind of read? Okay. After the superblock, we have something else. Let's go back to the notes here, but we'll go ahead and finish this part first. We have number of inodes per group. That is actually useful, but in the homework assignment, it may not be that useful, because we know which inode we're trying to access, and so it's not as useful. We have magic. That's useful. So we go and write that down. Okay. And then we have a few other things, but nowhere in here it tells me, where to find the block group descriptor table, or what a block group is. Okay, So let's switch back to the spreadsheet. After the superblock, or the block that is right after the superblock block. Okay, I know it's. Did you guys notice what I just said? The block after the superblock block, or the block that contains the superblock. Now, why is that not redundant? Why is there no redundancy in what I just said?
Because a super block might not fill up a whole block.
Exactly. Okay, the superblock itself is only 1024 bytes, and it starts at 1024 byte offset from the beginning of the entire partition. But the block size doesn't have to be 1024. It is at least 1024. It can be 2048. Can be any. It can be 1024 times 2 to the power of something, as long as it is not negative. So that means. Okay, let's just make this portion bigger. Okay, so we'll use sheet 2 to look at the first part of the entire partition. So we'll rename the sheet and say beginning of partition. So if you look at the beginning of the entire partition, if I use let's say 16 cells here to represent the entire first block. First block. Why is it doing this? Okay, let's try alignment, wrap, vertical middle, that. Okay, so this first block, is not our super block. It contains the super block. So depending on the size of your first block, your super block may actually be only using a very small portion of it. In other words, in this case, this is our super block. Can someone look at this? If everything is drawn to scale, what is the block size in this case? 49. Yep, exactly, 4 kilobytes. Okay, so this is assuming the block size, a block size of 4 kilobytes. Then this would be the map of the first portion of the entire partition. Is that making any sense? Okay, so what I should really also do here is to say this is our first block, but it is actually numbered block 0, because when we count the block ID, the block ID, when you read block ID in the documentation, it really is just the index into the file system, but it's counting only in terms of number of blocks. It's block addressable. So in this case, this is block 0. What do you think is block 1?
Next block after the block 2. Second block.
Yep, but what does it do? What is its purpose? It's a block descriptor table. It's the first block of the block descriptor tables. Depending on how many blocks you need, there will be 1, 2, 3, or whatever number that you need. Okay, so we'll just take.
To contain the block descriptor table?
Sorry?
There may be more than one block that contains the block descriptor table. I'm sorry. The block descriptor table may be contained in more than
Yes.
just the one block.
Yeah, but since our test file system is so tiny, everything is contained within one block descriptor. The block descriptor table only needs one data block. Okay. In fact, it only uses a fraction of it.
Is it broken up, or would it actually just span? Or would it be somehow segregated into those blocks in a special pattern, or would it just kind of span them?
Let's take a look here. So this is our second block, which is also called format cell, wrap text, middle. Okay. So this is actually our block 1. But block 1, also has a special purpose. This is our block descriptor table. Okay? In other words, if you know how to find your first block, then you will find out what the block size is. Once you know what the block size is, then you can locate the second block, or block 1, which is your block descriptor table. Now, the block descriptor table, each entry inside the block descriptor table is a block descriptor structure or record. So let's switch back into the notes here. Okay, we'll leave this one here. Let's see. Okay, we'll move this one. Oh, just open a new tab. Okay, one block group is basically one big chunk of your file system. And your entire file system is organized into block groups. So if I go back to here, go back to the first tab, that means your partition has the super block, and then the second thing, or the second blocks, sometimes it's more than one, would be your block group descriptor table. And then after that, you just have block groups after block groups after block groups. So you will just have block groups here. Just do a border. Oh, I have to select.
So in our homework, we found the block size, and then we found the block group number or block group size. Is that the number of blocks that get grouped together?
Okay, there's one field in the super block that tells you the number of blocks per block group.
Yes.
Or it can be computed either. So let's go ahead and take a look at that.
And that's what's confusing me. I don't quite understand that number.
So this is block group 0, okay? And then you have, the next one down would be block group 1, and then next one down would be block group 2, and so on. Now the file system that we have been using for testing was so small that one block group is already enough to contain everything. So we only have one block group in our case. But when your partition is big enough, you can actually have multiple block groups.
In our homework, the number is 8192.
Okay.
That's what I don't understand. What is that number?
What is that number? Okay, let's.
Our block size is 1024. I get that. It's the 8192 that I don't understand.
Our block group in the example is 4096.
Okay, this number tells you the number of blocks per group.
Yes.
Okay, which in our spreadsheet is the size of these rectangles. That's your blocks per group. So when you combine the block size and also the number of blocks per group, that tells you how big how big each chunk is for the block group. Okay? Is that doing okay?
So you multiply it, and that's the size.
Right.
Because it's telling you there's that many blocks.
That's the number of bytes.
Yes.
Because I'm already multiplying the block size by the number of blocks per group. So that's telling you the number of bytes per block group.
Okay, gotcha.
Okay. Are there any questions so far? No questions? Okay. So now when we look at each block group, we can take a look at how it is organized. Okay, let's see. Okay. This is what we want. Block group descriptor table. The block group descriptor table is an array of block group descriptors used to define parameters of all the block groups. It provides the location of the inode bitmap, inode table, block bitmap, number of free blocks and inodes, and some other useful information. Now, it's basically just a summary of how much of the block group is used. The block group descriptor table is located on the first block following the super block. Okay, so that we worked out already. This would be the third block on the 1 KB block file system, or the second block for a 2 kilobytes or larger block file system. Does everybody understand what this means?
So there's not a block group descriptor table at the beginning of every block group.
There's only one block
Block group
group
descriptor
descriptor
table.
table that allows you to locate all the block groups. And then each block group has its own inode table.
Okay, but they don't each have a block group descriptor table at the beginning
No,
of them. Okay.
no. The entire system has one single block group descriptor table.
Thank you.
Okay?
There's only one inode table per block group?
Yes. Okay, so we'll go ahead and take a look at the block groups with descriptive structure. And we'll switch back to the spreadsheet view, and then we'll just keep adding more stuff to it. So this I'll rename it as overview. We have the beginning of the partition. So now we want to take a look at the second block of block 1 and look at each entry of a block group descriptor. Okay, so here we have sheet number 3. The block group descriptor table has many items, but of all these items, the one that we are really interested in is number 8, or at offset 8. This is the block number of the inode table of this particular block group. Okay, so we'll take a look at this picture. Okay, what is inside the block group here? So sheet 3, we'll go ahead and rename this first. Okay. So this represents a block group. So if you look at the block group as one big chunk of memory, format. Okay. So within the block group, there are several things. You have the inode bitmap. That's one block. That's at least one block. You have several other things. But among these things, you have the inode table. So the inode table is one portion of an entire block group. Okay? There are other things, but we are not interested in the other things for the homework assignment. Does everybody understand what a bitmap is? Other than the context of a picture bitmap. What do you think this means when we have an inode bitmap? When I tell you one inode represents a file, a folder, or anything in a file system, what do you think an inode bitmap is going to be useful for?
It was stretching.
Oh, stretching? Oh, okay.
Is it telling you how many inodes are used?
It tells you, okay, go ahead.
Or does it tell you like what it is, what the inode represents?
Yeah, go.
I was going to say that it probably will tell you essentially what blocks an inode is using.
Exactly. Okay. Now, how do we know how many inodes there are per block group? Do we know that?
Back in the super
Inodes per group minus 3 inodes.
Well, if you look back into here, this tells you exactly what that number is, right? Inodes per group will tell you, how many inodes we're supposed to have per block group. Are we doing okay so far? Okay. So the next thing is, what is a bitmap? In this case, the bitmap has exactly this many bits. Okay, 1 bit represents one inode or one entry in the inode table. Okay, the first one, bit 0 of the entire table. Look at this as an array of booleans. Okay, it's an array of bits. The first bit or bit 0 is telling you whether inode 0 is in use or not. Bit 1 is telling you whether inode 1 is in use or not. In other words, it's just a whole bunch of zeros and ones, each one representing whether a particular inode is in use or not.
This S inodes per group, are we in the super block here?
Yes, this is the super block because it has a prefix of S underscore, and block group has a BG, as an underscore. I mean, BG underscore is the prefix of the block group designators. So are we still doing okay so far? Okay. All right. So looking at the block group descriptor structure, these are all useful. If you want to check whether your system is actually self-consistent or not, the bitmaps are extremely useful. Okay, how can you check whether your file system is self-consistent or not? Well, what you do is you inside the memory system of your E2FSCK program or whatever program that you're writing, you just say, okay, all blocks are not used. Okay, in other words, your block bitmap, you just have to mark everything as unused. And then as you traverse the system, starting with a root directory, you start to locate things within this block group, and then you track down each and every block used by each and every directory and each and every file. Every time you see, oh, okay, this data block is actually in use, then you mark it up here. You mark it in your bitmap. So that way you are basically doing your own accounting by tracking down how the file system is using all the data blocks. If there's a discrepancy, what do you do? If this bitmap here, the block bitmap, does not agree with the computed block bitmap when you're traversing all the files, then what are you going to do?
Override it with your own, because as long as you follow the specification, yours is right. That one is calculated literally bit by bit as you go through. But as the file system is in use. But if you go through and manually account for everything, that's right. Who knows why that's wrong? The one that's stored is wrong.
Yep. Basically, it's equivalent to the garbage collection process in Java.
And I just had an epiphany. So we're looking at this structure just for the first block group. But you go on, and there's multiples of these for each block group.
Yes.
So, okay, all right.
So each block group has one entry that is 32 bytes, and then each 32-byte structure is used to represent information that you need for the individual block groups.
And we're looking at the first one, which is the root directory.
The root directory is always in the first block group, is always the second entry of the first block group. So that way you always know where to find the root directory, because not knowing where to find the root directory can be a problem. Because that's where everything starts.
The second entry of the first block group is the root.
Yes.
What's the first one?
The first one is, it marks all the bad blocks in the system. Okay,
If we want to know what's going on with the root, we need to actually skip this first one and go to the second one to look at it.
No, not this one. We're not there yet. Okay, so if we look at the picture here,
Yes.
the super block is here, and these are structures of the super block. And then we have the block group descriptor. So the block group descriptor is really not a part of the super block. And I don't know how to draw another bubble, because it can only have one. It can only have one single bubble as the start of everything. So let's see.
Is that the block group? That's the block group descriptor table you're talking about?
I'm confused because I thought it was the second inode structure that.
But we are not even in the inode table yet.
We're just still looking at that block descriptor table.
I'm trying to think of a better way to draw the pictures. So let me try another method. Inkscape. I think this will work better. Inkscape. All right, so I think this is going to work a little bit better. So let's go ahead and try this one. Okay, so let's say this is our super block. So we'll go ahead and document this. Okay, so here is our super block. All right. The block group descriptor is adjacent to the super block. So now we will go ahead and draw the other one. We'll go ahead and change the color a little bit. this is our block group descriptor table. Each entry of the block group descriptor table describes one block group. Okay, so we'll go ahead and magnify just that portion. Okay. So
And
we'll
each
draw.
entry is roughly 30-some bytes, is that right?
Right. Mhm.
Okay, all right.
So we're using these lines here to represent that we are magnifying one entry within the block group descriptor table. And I'll also just use here and then just say this is a block group descriptor. Okay. Are we doing okay so far with the picture? Okay. Now inside the block group descriptor, there are several entries. There are mostly entries of block IDs. In other words, they tell you where to find, the first block of something. And one of those particular entries, if I want to draw a picture here, is the inode table. Go ahead and say this is our inode table, which is a block number. Okay. And that's basically acting more as a pointer than anything else. So we'll use a pointer here to point from here to an entire block. We'll change the end of the marker like that. So now we are here with an inode table. The inode table itself can span across multiple blocks, depending on how many inodes do you have per block group. Are we doing okay so far with this? Now the pointer thing is basically, this entry is a block ID, and then you use the block ID to find this block in the file system, in your, not file system, in the partition. Inside here, we have, each entry is an inode structure or inode record. So now we have to look at the inode structure and see what it looks like. I'm just looking at the overview here to see whether I have enough room for this, because this will take a little bit of space here. So I think we're going to run out of space, so I'm going to have to point this one to
Back to the inode,
oh, maybe
the middle block, the middle green block. Yeah. Okay, that number. Let's say it's a 4, and let's say we have a 4K block size. So then it would be 4 times 4K, would
Yes.
be your offset.
when you have to use a seek operation to go to the beginning of the inode table, yes, you have to remember to multiply whatever number is here by the size of each block. That will be the number that you use for your seek operation. Because the seek operation is byte addressable, but this ID is a block addressable ID. So you have to remember to convert those two numbers, by multiplying the block size to the ID, for this particular entry. Okay. So are there any questions so far with this? Yep.
So if I'm understanding correctly, that there are multiple inode tables, first of all, is that correct?
Yes.
So
Each block group has its own inode table.
So I want to find inode 42768. How do I do that?
Then you
Which
have
table
to
is it in?
then you have to find out which table it's in by dividing that number by
Inodes per group.
inodes per group. Then you can find out which block group is responsible for that particular entry. And then you use the block group descriptor table to index to the right block group first, and then from that block group descriptor, you go to the inode table for that block group, and then you use the remainder of the division to locate the entry within that particular inode table.
So inode numbers are, or inode IDs, if you will, are not arbitrary. They actually are linear and correspond to one.
That is correct. They're linear and they're unique within the file system.
Okay.
The inode number is not per block group. It is universal across the entire system.
Okay. Thank you.
Okay. The homework assignment doesn't have to touch on these things, but those are very, very good questions, because when you have multiple block groups, how do you order the inodes? Because now each block group has its own inode table. So do we string them all together to become one super long sequential one long sequence, or do we break it up? The answer is we string them all up and linearize everything.
Thank you.
Mm-hmm. So this is an inode record, or if you prefer, structure. And since I'm running out of room on this row, I'm going to start with the next row to represent what is an inode record. So over here we have an inode record. Oh, okay, that's the wrong tool. There we go. That's the right tool. This is our inode record structure. Are we doing okay so far? With how to locate, the items that we need to find. Okay. So we'll use our magnifying glass here. Take a look at this. Oh, bad spelling. There we go. Okay, so we're looking at one single structure now. And if you go back to the description here, we need to go find that entry as well. So keep scrolling down until you get to inode table. And on inode table, if you look that up, this is an inode structure, which is the last block that I write, that I draw, is this table here. It has it's broken up into multiple bytes. Each inode structure basically represents a file. It represents either a file or a folder or something that exists in the file system. Are we doing okay so far?
In the table, are there going to be there's going to be a sequence of inode structures?
Yes. Yes. In fact, if I go back to this diagram, go back to this thing here. So this is an array of inode structures. And in the other slide, this is what each inode structure looks like. Since we are already looking in here, so we'll switch back to this view here. Okay. The first few items are not really that complicated. imode is the first 2 bytes, and then it's basically a bitmap. If you look into what an imode is, it's a bitmap. The first few bits, the first 4 bits together, is used to indicate the kind of file that this inode is representing. Okay, so we'll just take a quick look at the highlighted portion here. We'll talk about these in a little bit more details later on, especially with a socket. But if you bit mask the most significant 4 bits of the 16-bit quantity, then you end up with the patterns of 1, 2, 4, 6, 8, 10, and 12 in decimal, because that's what A and C are. One is 10, the other one is 12. And these particular bit patterns will be used to indicate what kind of an object it is in your file system that this inode is representing. We can see certain things that we are already familiar with, like a directory and a regular file. But there are things that we are not so familiar with, like a symbolic link. Okay, we kind of talked about what a symlink is the other day. It's a way for you to link one entry in a particular folder to something else, that is somewhere else in the file system. It's kind of like a shortcut. You can also have a block device. A block device is a special file. It is not actually a file. It is mapped to a hardware device that is a block device. A char device is also usually an I/O device. So if you have a Bluetooth device, that would usually be mapped to a character device, or at least have an existence as a character device. FIFOs are basically pipes. They're named pipes. Okay. How many people know what a pipe is already, just using the vertical bar on the command line? Okay, so what a pipe is in a normal setting is just a quote-unquote file where one program can output to that file and the other program can read from the file. It is only intended for end-to-end communication. In other words, it's only intended for one program to talk to one other program, and that's the end of it. The bar symbol does not create a actual pipe that has a name. It is a nameless pipe, okay, because there's no need to know the name. But if you want to, you can actually create a named pipe where one program can redirect its output into that quote-unquote file, and another program can redirect its input from that file, and it serves the same purpose as a regular pipe. But because it is named, then your programs know where to find, and those two programs do not need to be started at the same time. Because you don't have to say program A, pipe, program B. You can start a program A, redirect to the named pipe, use another command line later on, and then say program B, redirect from the same named pipe. So this way it gives you a little bit more control in the system.
Would that be stored on the file, in the ext2 file system as
Yes.
a file?
Yes, it has an entry. It is a quote unquote a file, but it is a special file because it's a named pipe in that case.
I have to ask, why would you do that instead of redirecting output to a regular file and then redirecting input from that file?
Because if you do it that way, and one program decides to hang up, the file can get exceedingly large. A pipe, on the other hand, has a limited capacity. In other words, if program A, which is the one that is generating the output and dumping stuff into the pipe, if the pipe doesn't have anything to connect to on the other end, I think only one of two things can happen. Either the content is lost, or it will fill up the buffer, and then program A will be blocked. The operating system will say, okay, there's no more capacity. Stop, spewing stuff out to the output. So in that case, from that sense, a pipe is better than a regular file because, it stops the producer when there's no capacity left. It also blocks the consumer, the one that's reading. Instead of reading an empty file and say, oh, here's end of file, I'm quitting. It actually understands, okay, it's not done yet. I'm still waiting for the producer to produce more content. So it is quite different, on a fundamental level compared to a regular file.
Why would it be stored in the file system instead of? It confuses me that it would be a file system concept, not a kernel concept.
It's a file system concept because it's persistent.
True.
So once you create the named pipe, it stays there. The next time you reboot the system, it will still be there.
Okay.
So it's kind of like a file, but it is not an actual file.
Yeah, it just doesn't make sense to me to organize it that way.
It's a wormhole with a fixed coordinate. So every time you reset the universe, you know where the wormhole is.
Do you know any examples of a named pipe that exists standard on the system?
Named pipes are they're not used very often because a lot of times sockets are actually a better way to utilize. Okay, that's what a named pipe is. The whole concept of a pipe is you only have one program on one end of the pipe and one program on the other end of the pipe, and that's it. Okay, basically that's what a pipe is, right? One end as the input, one end as the output. So that brings us to a socket. A socket, on the other hand, is I wouldn't say it's an entirely different concept, but it can do everything that a pipe can and then some. Okay, what a socket is it's difficult to find a real life analogy because there's no such thing, in real life, in the physical world. Think of a web server. Okay, think of a web server program like Apache or IIS. Okay, does everybody understand what is a network connection? Okay, you don't even need to understand those terminologies. Just pretend that you are a program and you're responsible to serve out HTML documents. Whenever someone, a web browser connects to this computer, I have to return with an HTML document. Is that okay so far? Okay. So what if I tell you that this program can only serve one connection at a time? Well, some people will say that's not
easy to do a DOS attack then.
Yes. Well, the DOS attack will succeed anyway because the system resources is still limited. Okay. So let's say I'm the server program. Okay, I'm Apache, and all of you are client programs. Your browsers, are running on PCs. I'm the server running the web server program. Okay. So if one client connects to me and say, oh, I want to look at this particular document and give me the URL, it's okay. I'll go look up the document and I'll return the document. I'll reply the document to you so that you can render it on the screen. Okay, and I can do it on a one by one basis. So everyone, you connect to me, you request a document, I will give you the document, and then you request another document, I will go back, look for that document, make a copy, and then return that to you. What if both of you are making the request at exactly the same time?
Priorities. Like a queue.
Whoever gets there first.
Now there are different models. Okay, now there are different models. Okay, when the request comes in, okay, I can just decide and say, well, since I will only accept the first, connection, and I'll reply to the first connection. What happens to the second connection while I'm maybe you're requesting an HTML document or a zip file that is 1-point-something gigabytes. So it will take a long time to finish this transaction. What happens to all the other people who are trying to connect to the server? They're gonna have to wait. Okay? But that's not really acceptable, is it? So what we're going to do is to say, well, maybe I can just talk to all of you at the same time. If I can accept like 30 connections all at the same time. But how is that going to work? Because there's only one me here. Okay? There's only one me, and there are 30 people who want to connect to me all at the same time, and I want to be able to serve out documents and content to all 30 clients all at the same time. Well, the concept is a socket. From your perspective as a client, there's only one point to connect. It's port 80 of IP address blah blah blah. Okay, so each one of you as a client, there's only one point to connect. When you connect to that point, which is port 80 of a certain IP address, and I decide that yes, I'll go ahead and handle this connection, I will actually create a quote-unquote instance of that connection. Okay, that represents only that connection. So now the connection point, which is port 80 of the IP address, is ready to connect to another client. I'll create another instance to represent that connection. And now I'm ready to accept the third connection, and so on. In other words, if you want to look at this from the object-oriented programming concept, a socket is kind of like a cookie cutter. It's kind of like a class. You can use a socket to stamp out objects. What do you think the objects are representing?
Connections?
Yes. Each object is a connection. The socket from the server socket is nothing more than a class. It is used to stamp out connections. Are we doing okay so far? We'll talk more about sockets later on. But basically, that's what a socket is. So in other words, a pipe is cool because it allows two programs on the same computer to talk to each other. A socket is way cooler because it allows multiple programs to connect to a single program, potentially on the same machine, but potentially across the entire internet. And that's the power of socket programming, as opposed to pipes. Pipes only work on the same machine, but sockets can work across the entire network.
Do they have a socket class that we can take to learn how to use socket?
Well, this class will talk about sockets, just not a whole lot, but enough that you guys will actually be able to run simple client programs to connect to the same server program and be able to handle each client quote unquote in parallel. Okay, so that's kind of interesting. So that's what a socket is. socket, symlink, regular file, block device, directory, char device, and FIFO. We have just described all the different types of files that can exist in an extension to file system. The next part here talks about the permissions. Oh, this is about the process execution override, which typically are not really used anymore. It's called SUID and SGID, set user ID and set group ID. We'll talk about that later. It is useful, but it's not nearly as useful as these flags here. These are permission flags. In other words, who has what kind of access to this file? Yes?
On the left, on the constant names, is there a way to access those, or do we have to use the hard-coded values?
That's a good question. I think these are all constants defined, somewhere in a header file. So we'll let Google figure out, where.
I found the header. I haven't been able to figure out why I'm getting a compiler error, but I figured it out right as we had to leave the lab.
I think it's fs.h.
But if you're getting compiler error, maybe.
I probably made an unrelated mistake. I assume.
Yeah, ext2fs.h. But I think you have to have the source code of the kernel installed too, or at least the header of the kernel source code installed.
That's probably my issue.
Yeah.
So we're going to have to pound define these or do something if we can't get it in.
Or just use the values?
Yeah, just use the values again.
Or install the kernel headers.
Yeah, you can just install the kernel headers. It may be installed already too, because I have the cross-compiled NVIDIA drivers, so I think the kernel headers are actually installed already. We'll go take a look. It's kind of like a secondary issue. If not, you can just pound define those constants yourselves. We only need a few. It's not like we need like 30 of these constants all defined. We just need a few. So we can always just define the few that we need and be done with it. Okay. Now these are kind of interesting because they state who can access the file how. Okay, so both who and how are specified. Well, I shouldn't say who because a file is owned by 3 owners all at the same time. Okay, the 3 owners are called the user owner, the group owner, and others. The user owner corresponds to a user who can log into the system. Okay, so the user is definitely a user. The username after in your own last name when you do your homework assignment, that's a user as well. A group, on the other hand, is another concept. You can have multiple users belonging to a group. So this is a quick and easy way to allow multiple people the same kind of access to a file. In other words, if you have a top secret file that only people with sufficient clearance can access the file, you can go ahead and create a file, or create a group, You can create a group called top level clearance. And then you just add the right people to that group. And then in the group permission, you specify the correct access permission to that file. So that way you can control how a file is accessible to a particular group of users. It's really simplistic. In other words, it doesn't get to the same level as ACL in Windows. In NTFS, ACL stands for Access Control List, which gives you it's a very flexible way to control who can access a file. How.
They have that in Debian now.
ACL is actually in extension. I think extension 2 does it have it. Extension 3 definitely has ACL support, but it's not by default turned on.
Well, in Ubuntu it is.
It is?
Yeah, in Ubuntu
Okay.
it is.
In Debian, you have to do something to turn it on. Then you have generalized ACL, which is actually much better than just doing group access here. But that's basically what it is. And these are the values inside the I mode 2 bytes. In other words, if you just look at these 2 bytes, that's what it is. Yep.
So if a file is owned by 3 people, what the heck does chown do?
Chown can only change the user owner or the group owner.
Oh, okay.
Others refers to all the other people who are not the user owner or a member of the group owner. Okay? Okay, and the UID here is called a user ID. In other words, every user in the system is identified by a single number, and this number identifies that particular owner, user owner of the file. GID is the group ID. It identifies the group as the group owner of the file. And then you have A time, C time, M time, D time. They all represent different aspects of the time. Yep.
So does that mean you're limited to a certain amount of users in a environment on a machine?
You can only have up to 65,536 users. Yes. And root is user 0. You can deal with the user limitation by not using. No, there's no way to get around it because that's the system. That's a file system limitation. It's not even a how you log in kind of issue. Okay, A time stands for the last access time. C stands for the create time. M is modify time, and I is when the inode was deleted. When the file is deleted, that represents when it is deleted. Okay, so those are all kind of cool and useful, but we are not really using those. Blocks represents the total number of blocks reserved to contain data of this inode. Okay, so this is one other thing you can do a sanity check with, because you can also track down the size of the file using some other means. So you can do a cross check on the sanity of the file system. And then we have flags. Where's flags? Okay. We don't really need to use this, but it's, well, actually we do, because we need to look at, these two flags are actually useful. So we'll keep this screen open. Basically, flags, just give you some additional attributes related to the file. But what we are really interested in are these 60 bytes. Okay, 15 times 4 is 60. Yep, 60 bytes. So let's take a look at these blocks here. I block. Well, actually, there are 15. They're 15 times 32 bits, so there are 60 bytes. So we'll go back and into our documentation here, and we'll look at Inkscape. Okay, this is one record structure, and within the record structure, we have the blocks. Okay, so we'll go ahead and document this. This is the I underscore block structure. We have 60 bytes in this table. And this requires some attention all on its own. So we'll go ahead and save this file and open up another document. I'll call this extension 2. Create a new document. And we'll call this I block. There we go. All right. So this is where things get really, really kind of interesting. So here are the 15 entries that we have just talked about. And we'll go ahead and number the entries here. This is from index 0 to index 11 in decimal. In other words, the first 12 entries. The first 12 entries are not really particularly interesting, because each entry is a pointer. It's a block ID, and it's a pointer to a data block. Now, we talked about this last time already, so this part really should not be too surprising. ahead and just use a pointer here. And change the end. Now when I use an arrow end, it's not just for cosmetics, it actually means that we are using it as a pointer to locate another block in the file system. Okay. So now we'll go ahead and create a data block and change the color so that we can easily tell whether we are dealing with a data block or something else. Yellow is good. No, blue.
Why isn't there a black on there?
Because you can do it like this.
Oh.
You can
okay.
change the saturation and also the intensity. So there are different ways to specify colors. This is one way to do it. Okay, so we'll just call this, data block 0. Okay. And we can make things kind of a little boring here. What do you think this one is?
A pointer
Block
to the
Another data block 1, right? Data block 1 of this file. Does everybody understand what I mean by data block? If a block is 4096 bytes, what is this block representing? The one that I'm drawing right now.
497
Yeah.
Yeah, it represents the content of the file from offset 4096 to offset 8191, I think.
92.
91,
I'm sorry,
because
91.
it's
Yeah, 'cause it's
because
offset.
it's 0.
Sorry.
Yep, exactly.
Like you didn't know that.
Say that again. Is that because this is our first block in the
Hmm?
this or it's the blocks are 4096 in size, right?
Yes.
Blocks. And so what were you saying about the 8196?
Well, data block 1 contains the actual content of that file, but from offset 4096 to 8191, and those are in bytes. Because it's the second block of the file, and each block is 4 kilobytes.
Oh, okay.
Okay?
So this inode is representing one file.
One inode represents one file.
Okay.
And then the block portion of it, which is what I'm documenting here, basically tells you where do I find a particular byte, in the file.
Right.
Yep.
Just to clarify, from what she said, would it be the same if I said each inode structure represents a file?
Each inode structure represents a file.
That's
yes.
the same as saying each inode represents
Correct.
a file. Okay, thank
Yep.
you.
And these are literal addresses.
They are addresses, but they are block addresses, not byte addresses. In other words, this number here is a 32-bit number, but it is a 32-bit number identifying the block, not the byte offset from the partition.
So if we're dealing with 4K,
Mhm.
and that number's 20,
Mhm.
then it's 4K times 20. So again, we're all block
Correct.
referenced.
Yes. Yeah, these are all block addressable, not byte addressable.
Right.
Okay. So if my file is big enough, I would end up doing something like this. So I would use up all 12 blocks here, and then this one would point to data block 11.
Right.
There we go.
So they're not necessarily contiguous, is what we're saying.
You mean the blocks?
The addresses.
The addresses.
So like the light green on your left.
Mm-hmm.
Yeah, the numbers in here.
They may not be sequential numbers.
That's what I was asking. Thank
It
you.
would be nice if they were, because if they were sequential numbers, then
It
reading.
would just run through.
Yeah, exactly. Then you don't have fragmentation. But if these numbers are not sequential, then you basically have quote-unquote fragmentation when you have this file, because when you read this file, you will have to go to different portions of your hard drive physically to read the different portions.
I thought
Yep, go ahead.
If your file is less than this, are they just pointers to 0, or how do we know that?
Yes.
They're null?
It's in-
Yeah, what's in there?
It's in the spec, it's 0.
Just 0?
I think I remember reading that too.
And everything after that should be zero.
Yeah, it doesn't make sense to point back to 0 because block 0 cannot be a data block.
I thought ext file systems were supposed to be resistant to fragmentation, so
That has to do with the allocation mechanism and the freeing process, but it is capable of fragmenting. It does fragment too.
So all these numbers have to be 3 or greater, right?
These numbers have to be 3 or greater. It's actually more than that too, because you also have you still have the bitmaps for the inode and the bitmap block for the blocks and so on. So these numbers, should be a little bit higher than 3. Yep.
Is it possible for a single file to span multiple block groups?
That's a good question. I do not know. I think when you read the block group description, it actually tells you whether you can have a file spanning across block groups.
I think I remember reading something about that, and it said it tries to keep it in the same block group, but it
Meaning that it can go across.
If I remember correctly from what I read.
Okay. Now this entry is interesting. Entry 12, in the table is interesting because this one is a pointer. It's a 32-bit number identifying a block. But that block that it is identifying is not a data block. This is a block where the entire block are 32-bit block IDs to locate the actual data blocks. Okay, so if I were to number this, let's go ahead and change the color back to a green, and then draw a pointer. To here. Now this gets interesting because this entry here, the first entry of this block here, is pointing to data block what?
12.
Data block 12. Very good. So we'll put it up here, and then we'll replicate, fix the text first.
12 through 1036.
12 through 1024 plus 12 plus 11, because we are counting from 0.
Those are all contained in our first indirect block.
That is correct. Okay, so we'll draw a pointer from here all the way to here, and then we'll just document the first and the last item.
Like you said.
So this will be
1035.
Are we doing okay so far with these concepts? Are there any questions? Okay.
So each of the light green lines is going to give you 12, right?
Each of the
No, the indirect block that we've got going on. I'm trying to figure out the 12, how you got the 1035.
there are 1024 entries here, assuming that we have a block size of 4.4 kilobytes. Because each entry has 4 bytes, and each block has 4096 bytes. So that means each block contains 10,024 pointers, each one pointing to a data block.
Because they're 32-bit pointers?
Because they are 32-bit pointers,
And
yes.
it's a whole block.
And you have an entire block of these 32-bit pointers. But remember, when we refer to these as pointers, they're not byte pointers, they're block pointers. So you have to remember to multiply whatever the block size is in order to get the byte offset of the device. What about number 13?
It's a pointer to a block of indirect block addresses.
Yes. So if I just document here, because drawing this will take a little bit of time. Okay, so entry 13 in the table points to an indirect block. Each entry in the indirect block points to an indirect block, and you know the rest, right? Each entry in an indirect block points to a block. So now the question is, what is this doing to our file size calculation? What is the maximum file size when we have exhausted the 13 entry 13, I should say. Assuming a block is 4096 bytes. This 1024 times 1024, that's the number of data blocks we can handle just with entry 13. Are we doing okay so far?
So we get 4 gigs out of that.
So we get 4 gigs out of entry 13. And then the next one is going to add another 4 terabytes. Right? Because the next entry, or this is entry 13. Entry 14 is a pointer pointing to an indirect block. So within that block, each entry points to an indirect block, and then everything else we know already. But we already know that each block contains 1024 items, or 1024 pointers. So that means when we get to entry 14, we're adding 4 terabytes to the capacity of the file.
So why choose to have 11 pointers to data blocks and then have the last couple be pointers to indirect blocks?
I think they might have done some studying in terms of what is the frequency of file sizes, at least at the time when extension 2 was invented or was revised. They did some kind of study, and then they found out that most files fall within a certain size, so that you can use the direct pointers to point to the smaller to random access the smaller files. But everything is exponential. You can see that it is an exponential scale, and that means even if your file is really, really large, the number of indirect accesses when you get to entry 15, which is a indirect block, you only have 5 levels of indirection. So within 5 hops, you can get to a actual data block, which is acceptable compared to a linked list approach, which is going to be a whole lot worse than that when you want to do random access on a large file.
Can't do random access on a linked list. Can't do random access on a linked list.
Well, you can pretend that you have random access.
How?
You just do the seek operation. You just do it you just do it the long way. Okay. Now I'm not really done yet. We are running out of time. But to do your homework assignment, you really need to get it up to this point, because I think we have covered this material enough that we can at least locate the inode of the root directory and actually read the content of the root directory, because we have just talked about how to read the data blocks. Okay, so I want you guys to at least try your best to get that part done, so that in the next class I would assume that you can get the data block of the root directory in, and then the only question is, how do we parse that data to find out what entries or what files and subfolders do we have in the root directory. Okay, is that okay? Does everybody understand what we're up to now and what we need to do? Okay, all right. So I'll see you guys on Wednesday.
Next week, man. Or Wednesday.
Next week?
Once a weekend already.
In the Inode table where all the Inode records reside, how do we know how many Inode records there are here?
the super block has that information.
Oh, okay. Okay, that's fine. I'll look. I can look it up. I can go back.
That's okay.
There.
Okay, there's inode count, blocks per group, inodes per group. That tells you how many entries you have per inode table.
Okay, fabulous. Thank
And
you.
you have one inode table per block.
Yes. Thank you.
Okay.
Yeah, see,